Welcome to the last session. This is the first in the series of our summer education. I'm Thorsten Chlupp with Rena and Arctic Sun. I'm the owner. Today we're going to talk about passive solar, which is definitely one of my favorite topics. And Karl, my manager for Arctic Sun, will really take over and do this session for us. And those of us really have houses which completely rely on passive solar for 8-9 months out of the year, so we are really fond of speaking about it, and we're experiencing it every day. We see how well it works, especially this time of the year when it's really cold already, and a little bit of sunshine the last 2 days is plenty enough to keep the house warm. Pretty fantastic. And with all of that, I want to give it over to Karl. Thanks so much.
Well, good evening and welcome. Thanks for spending your Tuesday evening, or at least part of it here. I am Karl Kassel, as it says, and I'm going to apologize because I get passionate about passive solar, so if I get real excited, don't hold it against me. But this is my favorite topic. It's not one of my favorite topics. It is my favorite topic. So I enjoy talking about it. I hope you enjoy listening, and if we have questions as we go along, jump in. We'll try to answer them as we go. I don't think we'll be too tight on time, but we'll see how things go. So passive solar, this is a photo of my house, and this isn't a presentation about my house. This is a presentation about passive solar. So what I'm going to talk about is the passive use of solar energy and not all the really fun technical high-tech stuff like solar electric panels and solar thermal panels and all the other stuff that you can do with solar, which is really fun, and our company actually sells that stuff, so don't tell Thorsten that I'm telling you this, but that's the second part of the equation. You really want to start with passive solar, which is no equipment necessary. It's the only free energy that you're going to get, and I'm going to explain a little bit more about that. That's what we're talking about this evening. So even though I have a wind turbine at my house, and those are solar thermal panels on the roof of my house, and there's solar electric panels on the other side of my house, we're not going to talk about that stuff. And the figures that I give you and the numbers that I give you about how this works, this passive solar, it doesn't include those things, okay? So why are we going to talk about this stuff? Well, the cost of ownership of a building, what do you spend your money on over the life of the structure? And you're going to spend 84% in the operating costs. And we all know that energy is expensive no matter where you get it from, whether it's green or oil or whatnot. It's expensive. And that's what your house costs you mostly in the equation. So we're concerned about that, and we're going to talk about how we can save some money. Not only does 84% of your energy bill go into the operating cost. Take that back. I'm sorry, I'm getting ahead of myself here. The operating cost includes more than just the energy, but the biggest part of your energy bill is in space heating, as you can see in this graph. And that's something that passive solar can do a wonderful job with. So if you're looking at saving energy money, a real good place to take a look. So if you're looking about whereabout you might find some sources of energy, I don't know. These guys seem confused. I'm not confused. The sun provides a lot of free energy. This is a big number. I try not to use too high a technical terms, but Nathan, our lead designer, gave me a technical term. This is a shit ton. That's a highly technical term, but it's a real big number, and we get that amount of energy from the sun all the time, year after year, year after year. It's more than 10,000 times the amount of energy that we use around the world. For operating cars, homes, the whole 9 yards, the sun provides us more than 10,000 times the amount of energy that we need. So why don't we look in that direction more often? It's sad that we don't. For generations, millennia, we have previously looked towards the sun for energy. The Romans had laws, like zoning laws, where you had solar rights and your neighbor better not cut off the sun from your house. Because that was part of your heating equation. We've gotten away from that, and we need to get back to that. It tends to be a little cooler here in Alaska. I don't know if you've noticed, but it does get cool here. And a lot of people think that that's going to interfere with our ability to use solar as far as any sort of an effective dynamic in our equation, energy equation. Does it really work this far north? And I got to say, absolutely, unequivocally, it does work, and it works very well. And we're going to talk more about that. Part of why it works here, this is a slide some of you have seen before, but here in Fairbanks we do pretty good. These are numbers from around the world. When you look at the amount of energy that strikes the surface of the Earth, this is in kilowatt hours per square meter per day. It's an average number for the year. And here in Fairbanks at 3.48, we beat Anchorage. That's pretty cool. It's always cool when we beat Anchorage. We really beat Juneau. We beat Germany, where they have the most solar installed anywhere in the world. And we actually get more solar energy right here. So we can certainly do better than what we have been doing here in Fairbanks. So this is what we're going to be talking about, passive solar design. It's very simple. It's very simple. The part that I like the best about it is this free fuel part. I mean, it's free. And it's fuel, it's energy, and we don't have to pay anything for it. And when you use it in a passive system like this, you've got no moving parts, there's nothing to break, and you've got no maintenance involved. How many energy systems do you have that you don't have to maintain? Or they don't break down and there's no parts involved. And essentially, as we'll be talking, almost free to install. It just doesn't get any better than that. And the concept is so simple. We're going to let the sun come in our house. We're going to let it come in the wintertime, and not so much in the summertime because the sun's higher in the sky. We all know that. So if you have the right amount of overhang or eaves on your house, you don't get so much of this in the summertime, but you get more of it in the wintertime. When do you need the heat? Like right now. Are folks heating their homes right now by any chance? I can see that light is kind of terrible. I haven't heated my home since March. Probably won't for another few weeks, depending on what Mother Nature does. This works. It works real well, and we'll talk more about it. The concept is capturing that heat. It's radiant heat. We'll talk more about that too. You capture it, storing it in thermal mass to absorb that heat, and then give it back to you when you want it. There's no moving parts here. The sun comes up, goes around. We get cloudy days, so the sun isn't there every day. But that's when we get into storage capacity and how you balance these things. So let's do a little bit of science here first, okay? If you remember your high school physics, energy, or heat in this case in particular, moves from hot to cold. It always does that. Law of physics, you're never going to change it. So the cold doesn't seep in through the windows like people like to say, the cold seeping into my house. Actually, it's the heat is running out of your house. And so you want to discourage that. Heat moves three different ways. Conduction, like going down a wire. You know how heat travels through something that's metal. That's called thermal bridging in building terms. Convection, air moving around in your house like a forced air system where you're blowing air in and distributing heat that way. And the way that we're really going to consider this evening is radiation. I think everybody excuse me, understands the basics of radiation, but you really need to get a good complete picture of it to understand how and why passive solar works this far north. So radiation is the kind of energy that comes from the sun. Anything that is hotter than its surrounding gives off or radiates heat in all directions. The sun throws heat our way, as we talked earlier, in very generous quantities, and we are familiar with how it travels pretty much in a straight line. It follows and behaves like light waves. It behaves like a wave. You understand how a shadow does not get as warm as where the sun is actually hitting a surface. I think that's my next slide, as a matter of fact. So you absorb radiant energy, or energy is delivered and transferred, moved. We talk about it flowing. It doesn't stop until it hits something. So this radiant energy coming makes you feel warm even if the air temperatures are equal. If you're in a shadow or shaded area, you're not going to feel anywhere near as warm, even though the temperature is identical to where you're getting hit with radiant heat. That's important in the discussion as we go on a little bit later. This radiant energy that's coming to us behaves like light and is light related. Half of all the energy, the radiant energy that's hitting the Earth, comes in the visible spectrum of light. One thing that helps make this all work is that the energy coming from the sun is a shorter wavelength, which goes through glass real well, the bottom line here. Once it's absorbed in the house and it's re-radiated, that's hard to say, it comes out as a longer wavelength, which does not go through, thank you, Nancy. She's always thinking. It doesn't go through glass as well, so you're trapping it inside your house, the greenhouse effect that we're familiar with. And we don't like it in some cases, but for passive solar design, we like it a lot because it helps us in this equation. This also helps in design because you know where the energy is going. If you follow the light, you can follow the radiant energy. A lot of radiant energy you don't see, however. Half of it you don't see. You only see half, but the other half that you're not seeing in the infrared or microwave wavelengths and the X-rays is still happening. So right now, you are broadcasting radiant energy because you're warmer than their surrounding area. So you're radiating heat, every one of you, into this room and into the seat you're sitting in, the seat that's in front of you. We can't see that particular wavelength. It's part of the longer wavelength spectrum. But you're still radiating the energy. So radiant energy is leaving everything. It leaves perpendicular to the tangent of the surface, as you see the far arrow over here, of whatever object has this heat energy or radiant energy. It's affected by the delta T. We talk about delta T a lot. It's the difference in two temperatures. The difference is the delta T. So if our object is 100 degrees and out here it's 50 degrees, we have a 50 degree delta T difference in the two temperatures. The greater the delta T, the faster the energy leaves. So it affects how quickly an object radiates. Also, the surface of the object is important in that the denser, smoother, more polished type surfaces radiate energy more quickly than a textured type surface would. Okay? So that's important when we're designing how to store energy and move it and do different things with it. We want to control and balance that kind of an equation in the design. One thing that becomes important, Dan Givens likes this, and I think that's Dan over there. I didn't see him come in, but if you have a thermal mass that you want to store energy in, you can use a brick wall. Stores lots of energy. It's thick and it's dense. We'll talk more about that in just a minute. However, when a flat surface is radiating heat, it goes off perpendicular to that surface, so you get a straight wall of heat coming off. So if this screen is our brick wall, it's throwing heat straight out this way. And if I put something like me here and I cast a shadow, like the one behind me, that energy isn't going to go anywhere but to me. So if I'm trying to heat this room up, the floor is not going to get any heat because the stage is in the way. The ceiling's not going to get any heat because it's too high. The sun, our energy source, or our source of the radiant energy, it's not the sun, but it's casting beams straight out perpendicular to the surface. So you have a unidirectional heat supply going into your room. But let's say you hire a stonemason and he uses some natural rock and builds you, hypothetically, let's say planters in your house or a masonry heater or something like that. And the surface is really uneven and it's three-dimensional rocks. We're just looking at a cross-section here, obviously. So a surface like that is going to throw heat up, down, left, and right, and it's not going to cast a shadow in your room. It's also going to heat the entire room because you're throwing heat in every direction possible. So a little bit better way to distribute heat than using a flat surface. So passive solar, I think, is a no-brainer and is one of the best things ever for a home. Why aren't more people doing it today? Why were they doing it, and why did we move away from that? This is something that bugs me a lot. When you go to build a new house, in today's day and age, the typical pattern is what I call a social orientation. You are competing with the Joneses, you're looking at how the rest of the world is doing things, and you're thinking about fitting all of your equation, your house, into the standard building techniques and whatnot. So you go and you get yourself a book, The Ultimate Home Plans, or you get a Better Homes and Garden magazine, and they have house plans like this in the magazine. So you flip through and you find your favorite house plan. You say, here's a real cool house plan. You take that plan to a contractor and you say, well, I bought this lot and I got this plan, and you take the plan home and you have the contractor build the house facing the street, because that's a social orientation. This is how we do stuff. This is the model that we're accustomed to utilizing in our system. And it's not a very smart way to build a house. I'm sorry. It really isn't. You need to engage your brain a little bit more in the process. And you need to think about what you're going to get if you follow this game plan for building a house. What's the end product? What's it going to cost you today and over the life of the structure? Because there's better ways to do business. Right now, we don't spend much of our budget. This is the pie chart we looked at before. We only spend 2% of the cost of our house designing it. That's really not a big piece of the pie, obviously, here. And we're going to spend most of our money operating the place. We can do better. We need to think. We're actually evolving. And this subject, I think we've gone the other direction historically. We need to move that way and actually think a little bit better. We need to get a designer involved early, and we need an energy orientation for our building, not a social orientation. Now, these don't have to be conflicting things. They're not mutually exclusive. But when you make decisions and all the way through here, there's variables that come up, and you need to balance your scale and see which way are you going to decide to do something. If you start with a priority of energy, that's the your mindset orientation in this project, and you get everybody in the project involved, and they know that you want to save energy because that's the orientation on this structure. If you're the plumber and you're looking at two different pumps to put in, and one pump uses 30% of the power that the other pump uses, you spend the extra 5% to put the pump in that uses 30% of the energy of the other pump. So this guy is making decisions as your house is being constructed, and they're putting parts in. A lot of those decisions could or should even be made earlier than that in the design process. But you can see when you start at every step of this equation saving 20 or 30% in this process, you end up with a much more efficient product. We'll talk a little bit more about some of the other aspects of orientation and how this goes. You can build a passive solar design home in any style. I'm not saying build a house like mine. I'm absolutely not saying build a house like mine. It's a decision you make, what style you want. You can build any style home more efficient and from a passive solar positive perspective. So these people who say, well, I really want to be more energy efficient and all, but I don't want to live in an octagon-shaped house like you do. I'm not saying you need to. These homes can be every bit as efficient. Let's talk a little bit about my house and passive solar design. This is the basic plan for my house, looking in it. Unfortunately, this is part of the slide you can't see as well. This is climate specific. A big problem over history with passive solar design, and the reason it hasn't gotten more popular, is because you can't Walmart it. You can't put it in a box and say, this is how you do it. Because a design that works here in Fairbanks is not going to work in San Diego. It's going to be junk in San Diego. And a design that works in Phoenix isn't going to work here. And so we can't mass produce these things. And I can't tell you this is what you need, because not only are these things climate specific, they're very much site specific also. Where in Fairbanks do you live, or North Pole? How much sun do you get? Where does it come from? Does it come in the east side of your property, or does it come in mostly from the west side or the south side? All of those things are going to enter into the design of the house. Material specific. What are we going to build this house out of? It makes a difference to what the design is going to be. So you've got to factor all of these different things in, and you certainly can't ignore the owner specificity here. Some people like pink houses. Some people like wood houses. So the owner of the home is going to decide some of these other equations. They're also going to have an impact. Are you a morning person or are you an evening person? That makes a difference in a house design, and it makes a difference in how you're going to gain this energy from the sun, how you're going to make it work, where you're going to use it, how the space is going to relate to you, and how you are going to relate to your space. So many people don't think about that in building a house. They're back to the Better Homes and Garden plan, where they find a nice little blueprint. And they take that house plan or blueprint and they think, wow, this is going to be great. And then they stick it on their lot facing the street. And they're not a morning person, but they like to stay up late and party. But the way this house is built is the sun beams in first thing in the morning, because the big windows happen to be facing to the east, because that was where the street was. So the social orientation that we talked about earlier ends up messing you up, just because with your particular lifestyle, the design of your home isn't matching that. And the way we're trying to get solar energy into it isn't matching it. So all of these different things go into how you're going to design a house. There are some givens with passive solar design. You want to bring solar energy in. Most of it comes from the south, so you're going to get a lot more. In this particular design, this wall, this door faces due south. So we're bringing some morning sun in through this window. All day long we're bringing in sun through here. And then later in the western, southwestern face, this is all glass, and this brings lots of light in. All of that light goes into one area. All that energy is dumping into this big open space, which is full of thermal mass, absorbing all of that heat, and we're storing as much of it as we possibly can. That's kind of the boiler room for a passive solar house. There's lots of ways to do this. This is one way of doing it, but the concept is passive solar energy into your storage area, the storage area being linked to the rest of the house as efficiently as you can, and this main part of the storage system as centrally located as you can. Now again, there's not one way to do this, but it's the concept that you need to grasp. Energy in, and then save it. And we'll talk a little bit more about that too. So, the concepts here. Solar gain we just talked about. We want the sun coming in. I moved south. Now south's at the top, I'm sorry. This is the back of the napkin. This is, again, my house. Concept here is we need to maximize the solar gain. You need thermal mass for storage, and you need an efficient envelope. We've had presentations about efficient envelopes, and we're not going to talk really about that at all this evening in any depth. We will talk more about thermal mass and the solar gain, but those are the three main components. And people say, well, a passive solar house like yours is going to cost me a lot more money because you have a lot of insulation. I do have a lot of insulation at my house. I have a very good, efficient envelope. It sort of has nothing to do with passive solar. It has to do with it gets cold around here, and every house should be well insulated. And your money is best spent on insulation. So this isn't an extra for a passive solar design. This is you put your money there and you do the best you can with that to begin with, period. Whatever kind of house you're going to build, because that's going to save you the most energy right up front. Build a good envelope. Make sure it's airtight. And if you don't understand those concepts, go to one of our lectures about those concepts. But it doesn't cost extra to go with passive solar design. No more money there at all in that equation. Thermal mass could cost you a little more money. Depends on how you're doing it, how you're accomplishing that, and we'll talk about different ways of doing it. I don't think it cost me any more money. I didn't spend a penny in my house specifically for thermal mass. I did things in my house that created thermal mass that were part of the design of the house that I liked and was going to do anyway. So that cost me nothing. And the solar gain costs essentially nothing. Solar gain is putting the glass in the right place, and we'll talk about that a little bit more. But in this house, all the glass is across the south side, essentially. There's a small egress window here for this bedroom, and there's one in the master bedroom. Nothing on the north walls other than a little decorative octagon-shaped window. So when you decide to finally build this plan, if you're standing where the G is in dining room, that's the inside of this room. And so we've got a lot of thermal mass. We've got a masonry heater in the middle of the house, which is lots of nice river rock, and is the only heating supply that I've used for 3 years here. We've got more thermal mass underneath the kitchen island. There's rocks over there. And we can't see. There's some more rocks over here and a planter in this corner. There's planters over here that go all the way to the floor that are full of dirt because the plants like the dirt, and I like the thermal mass because that dirt is all storing heat also in the house. So we decided we're going to do a passive solar type home, and back to our thinking, our orientation when we make decisions on how we're going to build this house. First thing we're going to do is not go down and buy the plan book, because the plan book is, I'm going to back up here. I've missed the most important thing on this whole slide. Right up here. Most people spend 2% on their design. Most people leaf through a few books, might spend a week or two even thinking about it and whatnot. It's a fairly quick decision. I started on the back of a napkin. This is one step up because it's actually graph paper now, a picture of the graph paper. But I started with plan A. And then I went to plan A1 and 2 and looked at those. And then I went to plan A2, A and B and C, and we played with those different dynamics. Then we threw those away because plan A just wasn't cutting it. We couldn't fine-tune it to where it needed to be for one reason or another. There was some sort of a poison pill. So we went to plan B. Plan B didn't get too far. We had plan B1 and B2. I don't know if we even got to plan B3. We had some 2 A's and B's. But anyway, then we got to plan C, and we worked on that for a while, and a few more levels of that. Some part of this equation, I think it was around plan A or so. I guess a little bit of history with me. I didn't work for Arctic Sun. It didn't exist back when we were doing this. I didn't work with Rena Construction Company. I had decided I was looking for a contractor when I had plan A in my hand. Somewhere around the end of plan A, beginning of plan B, I actually went to Rena Construction Company and said, hey, Thorsten, will you want to work with me on this? And his eyes lit up, and he said, yeah, this looks like a fun project. Let's do this. So I got him involved, and we went through plans B and plans C and plans D, and we had D1, and we had D1A and B and C. Obviously, this is a long story. The bottom line of it is we finally built plan D3B is where we ended up. So a lot of thought goes into the planning aspect of these things. A lot of changing, drawing pictures, three-dimensional, thinking about it. Going to the house site, I camped out on my house site and watched the sun and thought about this house plan. And what's this going to look like when I'm in the living room and the sun comes up over here? And is my kitchen going to be nice and bright and cheery in the morning to help wake me up with my coffee? Am I going to get nice evening sun coming in and see the sunsets off to the west? I mean, how is it going to feel? We thought about that from the tent while we were camping there. So you can't waste time thinking about all of this stuff. And the first thing you need to think about is basic as in our social orientation, the all-American home, the big rectangle. And is that efficient? These three shapes are the same size, same square footage. So the perimeter, if it's an octagon, is 160 feet around the outside. Same size house. If it's that shape, it's 195 feet. And if you do your math, that house has 35 extra feet of wall space around the outside. Where do you lose your heat in a house? Through the walls. And so, which is going to be more efficient from an energy heating perspective? Round is perfect, but it's hard to build. You saw in that earlier style slide that one guy had sort of a corrugated round house. I thought that was kind of cool. From an energy perspective, super design. Construction perspective, not so good. These are a little harder to build. Your carpenter better be good with math if you're building this over that. But you save material, so you're going to pay a little more in labor, a little more complicated construction-wise, but you're also going to build 35 feet of less wall space. And for the life of the structure, you're not going to lose heat through 35 feet of exposed wall on the same size house. So just picking the shape of the house, even square is better than rectangular. The more you elongate the rectangle, the worse it gets in the math equation. So it's just something to think about as far as efficiency and designing a house from a passive. Just let it sit there, and how is it going to heat? How is it going to respond to its environment? The shape's important. The orientation's really important. This is my living room, and again, that door faces due south. This was taken noonish time in the spring, still snow on the ground. And you can see the sunlight, how deep it penetrates into the house, way down to here, through the whole picture. Part of the concept of bringing the energy into the house. Thermal mass in the floor. This is a stained concrete floor. No covering on it. It's going to absorb heat quickly and store it in the concrete. It's also going to store it in all those rocks, the rocks in the kitchen island and elsewhere. How important is orientation? You really need to be due south with most of your gain plus or minus 10 degrees. Because if you get off 45 degrees, you're going to only get 70% of the solar gain through the same windows. And so, again here, we're talking, there isn't one way to do this, and your lot may or may not accomplish the perfect angle. But as you're designing the home, you have to factor in this guy is going to get 30% more heat for free than this guy. Same house, identical house, one guy gets an extra 30% worth of energy off of the sun, which is significant. We'll talk about the amount of these energies in just a minute. So it's food for thought. This is food for thought when you're buying a piece of property to build a house, not after you bought the lot, but before you buy the lot. Because if the neighbor lives right here and your lot line's right here because you have a long, thin lot this way, and these are all trees and you're not going to get any sun, you got a problem on your hands. So maybe you don't want to buy that lot. You know, maybe the street's on the wrong side of the lot if the street's over on this side of the house. So maybe you want to buy it where the street is going to be over here and there's no trees in the street and you're going to get a little more sunshine. This slide's real complicated, and I know you can't read much and you don't have to. It's a real basic representation. This is from Passive House Computer Modeling. What we've done is model many different aspects of the home from the window placement, and notice windows are separate for the west, the south, the east, and the north side of the house, because we'll talk about that a little more important, some of the aspects of that and why that's important later. This model is so sophisticated that it ranks the windows by the direction they're pointed. Thermal mass, heat recovery, all sorts of different things. The way this graph works is that this is the structure as it's designed right here. If we change any one of the parameters one way or the other, either improve it or decrease it, you can see what it does to the energy consumption of the house. This is 1,350. This is in kilowatt hours per square meter, I believe. Yes, kilowatt hours per square meter. So if we're on this line, we're at 1,350. So this structure as it's designed is at about 13 kilowatt hours per square meter per day. It uses more energy going that way and less energy going this way. Most of these lines are fairly flat or going downhill, using less energy as we improve the dynamic and using more energy if we decrease the dynamic, like putting windows that aren't so hot. Then we go this way. There's one line that's different, this one. This one that goes up over here, comes down, and then it goes back up over here. It's kind of strange. That's the orientation of the building. So this is a model for a house. If we take the same structure, just like kind of in the last slide, and turn it, what is the energy usage on an average basis for that structure? And it varies over 41%. If it's pointed due south, which is actually over here on this curve, we're at 1,300 or 13 kilowatt hours per square meter. It goes all the way up to over 1,850. We're up at 19 something, as I recollect. I forget the exact number on the slide, but over 40% increase in energy required for space heat. Same structure, just turning it. Is passive solar important? You want to save 40% or almost 50% on your space heating bill? If you could pick your house up and turn it around because the street's on the other side of your house or whatever. I mean, this is what we're talking about. It's a significant figure here in Fairbanks. Thousands of dollars annually, potentially. And back to no moving parts, nothing to repair, nothing to fix, same house, just spin it. Kind of interesting stuff. So, let's talk a little more about thermal mass. That's my masonry heater, and there's a lot of rock in there. A lot of rock in there. And we don't have just that, we have more thermal mass. I'm a firm believer in you can't overdo thermal mass. I haven't found the limit on thermal mass and its applicability for a house yet. It's just storage capacity. You can always use more storage, right? You can build a garage and your garage is instantly full, and build another one and you fill that up. Thermal mass is kind of the same way. I don't think we found the limit for it yet, and I don't think that my house is maxed out on it, and I've got a lot in it. There's a lot of different ways to store thermal energy. This slide shows the volumetric heat capacity. People are always thinking about, oh, if I use this material or that material or what I could store more or less. This tells you water is sort of the gold standard. There's two ways to measure the specific heat or the energy density. There's all different terms for this stuff, but it's essentially how much energy you can store. How big is your battery? Well, how much energy can you stuff in there to then get back out later? And water is considered the gold standard. Okay? You can measure specific heat by either weight or volume. This chart is volume, which is why I use the term volumetric heat capacity, which is really common. To me, it's a little easier way to compare different types of material in our mind. And so water's really good. It's 100%. Cast iron's really good. Maybe if you owned a junkyard, you could put a bunch of cast iron in your house. It would hold a lot of heat. Concrete is pretty darn good. Granite and the different rocks are, all these numbers are variable to a little bit one way or another. The rocks range from anywhere from like 40% to 49%, as I recollect. Soapstone, that people hear of a lot for masonry heaters, is really good. It's towards the higher end of the spectrum. I don't like it as well because soapstone's flat. And remember, when you're talking about radiating heat into a room, which is what you're trying to do off of a masonry heater, that flat surface of the stone is going to throw heat more unidirectionally than disperse it around the room like river rock. And call me cheap, river rock's a lot cheaper too, and we don't have to import it from Europe, so it has other advantages. Brick is pretty good. Rammed earth, popular with a lot of the green homes and whatnot. And even wood isn't too terrible. The problem is getting enough of it. And therein lies, enough of it is really the key with thermal mass. In some of the solar books that you read, it talks about using thicker sheetrock to store energy. Well, yeah, okay, that's going to store some more energy, but how many BTUs are we talking about? What's the mass? What's the overall volume of using thicker sheetrock in your house? It's really not going to get you where you need to go. Particularly here in Fairbanks, you need to store a lot more heat than in the lower 48. Back to the climate specific of the design and whatnot, we need some more storage capacity because it's cold around here. So how does it work? The sun beams in the window, we absorb the heat. If we have more than we want, we can flush it out. Even during the day, you can open windows and regulate if you tend to be overheating. If you overheat too much, which was a real problem with passive solar design originally, I got to tell you, you've got a poor design. You know, we're just balancing numbers here. We got energy coming in, we got energy going out. If you got too much in, then you didn't build it right. You got to work on the design. So spend more time on the design, get the design right, build in some flexibility so that you don't overheat. But we can waste heat by opening windows and flush some of it out, and the energy that we stored in our thermal mass radiates back into the structure during the day. Now, what does that do? This is a generic graph that shows as the air temperature is fluctuating wildly in this chart. If we don't have the dotted line, if we don't have a lot of thermal mass in the house, we're going to still even out the swings in the daily temperature swings. But if we add a lot of thermal mass to it, the equation, we really flatten that curve quite a bit. I'll go to the next one. This is conceptual, okay? In reality, what happens looks more like this. The thermal mass, or the rocks in my house, are such a huge energy sink that they just sit here on the dark line, the red line. I'm colorblind, I think that's red, right? That's the temperature for the rocks. And it's hard to make that temperature move. The air temperature, if we look at, this is a one-day cycle. So in the morning, it's cold out. The temperature, this is the air temperature inside the house. The outside temperature is cool. When the sun comes up, the temperature starts going up inside the house. We're gaining energy. The temperature in the house will continue to climb until we get up to about 76 degrees. And what happens is we get enough delta T here that these rocks are absorbing that heat. And it takes a long time, as they keep storing energy in the rocks, this temperature doesn't go up very fast. And it won't let this go up because as the temperature tries to go higher, our delta T gets bigger and we transfer more energy into the rocks. And so we tend to hit a plateau, and it's not absolute like this, but I'm trying to give you the concept here. The temperature will level off, and then when the sun goes down, then the temperature drops fairly quickly and rapidly. But it stabilizes because now all of the energy we stored in here is coming out here, out of these rocks. It takes a long time to drain it, and they only drop a little bit because this amount of energy, because it's condensed in the thermal mass, is heating the house all night. Okay? Let me talk about this other thing here first. There was a lot of research done about thermal mass, and does it really save your heating bill, all this thermal mass? And it was maligned quite a bit because they said, well, we tested these homes and it didn't have a significant effect on our heating bill. And I looked through a lot of that research, and I find that on one hand, it's absolutely accurate. But on the other hand, if you're living in this kind of a house and you understand this particular slide, then you change the way you operate your house. In a normal home, when the temperature starts to cool off, the heat kicks on. And it won't let the temperature drop to 70 degrees because you got the thermostat set at 72. And so here, the thermostat kicks on in your house and you're going to heat it. So what you need to do to make thermal mass be efficient is you have to allow a little greater daily swing in temperature. Now, I live with this, and I do not find this to be remotely inconvenient. How many homes go into the 80 degrees or 90 degrees inside during the day? My old house used to. Didn't have as good a solar design, and it didn't have any thermal mass for storage. So during the day when the sun came out, boom, we were 80, 85, 90 degrees in the house. That doesn't happen if you're storing that heat here. You hit this plateau, and you don't get crazy hot because you're storing that energy. So it really helps you in that equation. The same thing when it cools off. You know, if you set your thermostat to kick on at 70 as soon as you hit 71 because you want your house to stay at 72 degrees so the heat kicks on here, you're not letting the thermal mass work. And you're not going to get the heat out of it because if the air temperature is just trying to equalize and our thermal mass is only changing a degree or two, and our thermostat's kicking in here, we're not utilizing that mass. Okay? That's real important because if you're testing a house that has thermostats with a close setting on it, you won't see the value from the thermal mass. You got to let it do its thing. What happens on a 4-day cycle? Because boy, here's today. Boy, we got some energy today. But maybe tomorrow it's going to be cloudy, and the next day it's going to be cloudy. So this is a 4-day cycle. We got 2 nice days, and if the sun doesn't come out for a while, we slowly start to lose energy out of our rocks. Every day we're going to lose a little bit. And that's going to have a corresponding decrease in the lower the temperature is going to be in the house. And at some threshold, and in our house we use the 68 degree threshold. If it's 68 degrees when you go to bed, or 67 degrees, then it's time to light a fire. Okay? That's just how we operate. And my wife's here, and she'll agree that I keep our house too hot. She would keep it cooler. And we had a discussion the other day, by the way. You got to agree in the family about how you're going to operate your house. Because we're storing heat, right? Right here. And totally hypothetical, I would never bring personal discussion into this, but let's say, hypothetically speaking, that your wife gets a hot flash right around here. And so she says, okay, I'm going to open all the windows because I'm hot, and the house is kind of warm, and I'm going to open the windows up. Like yesterday, let's say, hypothetically, and I'm saying, there's snow on the ground at our house. It's like cold out. Let's not have the windows open and waste this heat. We're trying to store the heat in the rocks here, so let's close the windows and keep the windows closed, please. Anyway, Totally hypothetical situation. But you got to think about it when you're dealing with this. You got to be able to deal with the temperature swings a little bit. I don't find them extreme at all. I think our house is more comfortable to live in. And my charming wife, Billy, who's I think still there, I can't quite see in the back, and I frequently comment to each other, our house is amazing. We've been in it for 4 years. It's amazing, and we're still amazed. We sit in our living room and go, this house is so comfortable. Why don't more people live like this? And we're dealing with these temperature swings. And you don't really notice them because when the house is well insulated, it keeps a good average temperature through the whole house. And so you don't get drafty areas and those sorts of things. So glass. Glass doesn't need to be a ton of glass. The books will tell you 10 to 15% of the square footage of your house should be dedicated to glass, okay, to make passive solar work. If you're a normal house, you would be 9 to 13% would be typical for American-style home. So slightly more. However, I got to tell you, if it's designed properly, my house is 11%. It's not more than average. It is average for an American home. And I'm getting plenty of solar gain at my house. So if the design is right, it's going to work for you without huge expanses of glass. Does need to be the right kind of glass, though, and all the glass in your house should not be created equal. The glass on the north side of your house should not be like the glass on the south side. On the south side of your house, you want a good solar heat gain coefficient of at least 60%. 100% would be letting all of the heat in. You want to let heat in. That's the solar heat gain coefficient. You need a minimum of 60% and minimize, I wouldn't say no, but minimize windows to the north. They're not helping you. And so you need decent windows, like triple panes are quite helpful. Preferably fiberglass frames, and I'm not going to spend a lot of time on windows and how they're installed. That's a different lecture. But again, you want a good R value or U value when it's windows, and a good solar heat gain coefficient on the south side to make sure you're getting that energy in the house. The design should include a good penetration of the sun into the house. This picture was taken early in the evening, and you can see the big west window over here. The sun is coming in that window and coming all the way across the house. This is the mullion in the window casting a shadow on the kitchen counter. And we're lighting up the kitchen cabinets, which are over here, clean across this room. And if you had a tape measure and you measured from the kitchen cabinets over to that window, we're at like, that's 40 feet in my house. So the sun is really beaming through the window. That's part of the design. That's part of how it works. That's part of capturing the right amount of heat. So how do we not overheat in our house? And how we don't overheat is partly because this is an awning frame that in the summertime I run this awning out 4 feet from the house across this frame, and I decrease the solar gain coming in this great big window. This window is 18 feet long and 6 feet high. And so we decrease the solar gain by putting an awning across it, and I do that seasonally. We don't have it up right now because we're trying to maximize the solar gain. And I forgot on the other slide at the bottom, if you read it, you already know this, but we don't, from just passive solar gain, with balancing it, this equation, somewhere early March, the first year we lived in the house, it was March 6th, we quit lighting a fire. That was the only way we heat our house. Yes, I have all these other energy systems. They're not part of heating my house. We stopped heating the house first week of March and didn't heat it again until October 10th. Just over 7 months, no heat. Are you heating your house? Today? Yesterday? The day before? We're not. And haven't since March. This year we didn't heat for about a week and a half, the end of February, early March, and then we had really crappy March weather, if you remember, and we didn't get much sun. It was really cloudy. We actually had to light a fire March 14th, I think it was, or 15th, and I was mad because I broke our string. But we got colder than 68. That's my bottom line. Lit a fire. So by regulating the amount of solar gain like this, we keep it within that window, 76 to 68, and stay in there with no moving parts and no other systems. This is a real crappy solar design because we're getting way too much gain, and no place to store it, and it would cool off in a hurry because our envelope is terrible. So the design, again, is important. This design, not too hot because we've got big windows up high to the east. We're going to lose heat out there, and they're not going to give us the gain we want. We've got a fair amount of glass on the east side. I'm assuming that these two-story windows are to the south. We have no way to regulate the gain over here because an awning isn't going to do us diddly 2 stories up. We're going to overload with heat through the bottom windows here. So we've got way too much solar gain coming in on this and no way to regulate it or control it. So we're going to overheat, and then we don't have really too much thermal mass. We've got some wood in here, but not really enough storage capacity to balance the system. So these are kind of some earlier passive solar designs and why they don't really work here. So summarizing a few things, we want to really maximize the passive solar, bringing in essentially as much energy as we can. We want to keep it. These are just, people are always asking me about wall values. This is what we recommend as minimum insulation values, minimum, okay? People think these numbers are crazy. We absolutely don't think they're crazy at all, and we recommend even going better. These are minimum again. No thermal bridging, conductivity through your walls. This is air changes per hour. You want an airtight home. And all of these factors should be in your house anyway. So they're really not part of passive solar design. They're part of good construction in Fairbanks, Alaska. But they're part of the equation. All of the parts add up to making this work. And you need all of this stuff to make anything work in Fairbanks. And it really can maximize the passive solar if you do those things right. So the new tools of the trade, we want to make sure we're airtight. And so we're using blower door kits and anemometers and checking air movement and infrared cameras. Oh, I was going to bring mine to show you. They're so much fun. I drove my wife nuts going around taking the temperature of rocks in my house. See, an infrared sensor to point, just like this pointer. You point it at something and it'll tell you the temperature of it. And I was tracking individual stones and keeping it on an Excel spreadsheet. All right, I'm a little anal, but forgive me. But going around the house and doing that and watching this dynamics of the thermal mass and how it stores the energy, and which rocks got hotter faster, which ones got hotter totally, the speed, the volume, the amount, total temperatures, all that kind of stuff. It was fun. And it helped me understand, because I'm kind of that sort of a visual kind of a person, how all this goes together. This is a little fantastic little computer device that tells us how much sun you get. You just take a picture with this fisheye lens, hold it out flat and level, and it'll tell you what kind of solar gain you're getting at that exact spot. Kind of fun stuff and real important when you're trying to design this sort of thing. So does this stuff work? Okay, so this is my house. This is some numbers from the first 3 years of living here. It's a 2-bedroom home, 1,860 square feet. There's 3 people. That's cheating. There's really 2.5. I have a son that's there week on, week off kind of deal. But so there's 2.5 people in this house. And for the whole winter, for heat, space heat, 2 cords of firewood. And because the masonry heater in the firebox over here has a heating coil, we heat our domestic hot water when we're burning a fire in the masonry heater. So we're doing double duty. So this 2 cords of firewood not only heated the house for the entire winter, it also heated a good portion of our domestic hot water through the course of the winter. That's a pretty low energy bill for a house in Fairbanks, Alaska. That's on top of a hill and exposed to the wind in particular. We also, because we're off grid, burn 20 gallons of diesel fuel for our backup generator when the sun and the wind were not accommodating us. And we went through about 150 gallons of propane because we cook with it. And propane is backup in our house for all systems. When all else fails, our house would run like a normal house using propane for energy. But we really don't get there very often. And never for space heat. We've never used that aspect for space heat in our house. So this is 100% of our heat. So it's all about balance. You got to balance all of these equations. What do you like? What do you not like? For materials, style of your home, and all of that, all of those owner-specific questions. And balance those with all the energy ideas that we're talking about. The windows, how big are windows, the placements, all of these things. There's no one way to do this. It's design it for the site specific, your interest specific, and balancing all of these different things. It's fun. It's a challenge, but it's fun to work on. And when you're done with it, you have a product that is really you feel connected to and part of, because it's more than just a house when you design a house this way. It's a much better way to live. And the orientation to the planet is more important than your orientation to your street. Trust me. And it can save your wallet in the equation also. So it's all about balancing these different aspects in the building. So remember that passive solar is the only free energy that you're going to get. And if you don't take advantage of it, I think you're being foolish, because here in Fairbanks, it can be huge. 40% of your heating bill or more gone. That's, to me, pretty incredible. Certainly part of it is the efficiency of your envelope and that sort of thing. But as we talked in the orientation slide, just moving it, the passive solar is really the key to all of this. And you can boost that dramatically with some of these high-tech systems, and I'd love to talk about solar PV and solar thermal and the fun stuff you can do with all that, because that's really cool and it's high-tech. But really for me, what's important is the simplicity of passive solar. I'm the kind of guy who just thinks that simple and straightforward is better, and not having things that break, because I'm not a good mechanic, and it always breaks when it's 40 below zero. That's a rule here in Fairbanks. And so then you're fixing stuff at 40 below. There's nothing to fix with this. And it takes a huge chunk out of the energy bill and affects the way you live. It affects the way I live. I'm more in tune to what's going on with Mother Nature and the temperatures inside and outside, and planning ahead and watching how this delicate balance of my house interacting with the environment that it's sitting in. And to this day, after 4 years of living there, it still amazes me and my wife when we just think, we haven't done anything in our house to regulate the heat other than opening windows and closing windows. That's our involvement with this equation. But the comfort level that we have exceeds most homes, and we're still not heating our house this year. So anyway, you can tell I believe this stuff because we live it. Thank you. We have more information on our website, and that's our website, arcticsun-LLC, or you can go to RENA-LLC.com also for the construction website and get more information about fun stuff, or give us a call if you have questions. And we're Arctic Sun and we're RENA Construction, and I want to thank you for your time. And I'm available for questions, because I'm sure that folks have some questions about this stuff, and we do have a little bit of time for doing that. We've got a good 10 minutes that we can do for questions. So, questions from anybody? Yes?
On your windows, have you ever considered some way to minimize heat loss through them at night?
Oh yeah, there's all these great topics. Definitely. And there's no way to really get a house to the efficiency levels that we like to see, passive house standards. We didn't talk about that in this particular presentation, but you really need shutters. There's not a window made anywhere on the planet that satisfies the kind of R values or U values that we need here in Fairbanks. And so you have to go to some sort of a shutter system. And funny that you should ask. I didn't pay you to ask, but we did get a grant from the state, and we're taking a look at that right now, and we're designing a couple of different styles of shutters to work on this, because really you do need to have them to maximize efficiency. So we're looking at movable rigid shutters, and we're also looking at a little more high-tech blowing in foam pebbles into a cavity outside your window to provide about 4 inches of insulation and then blowing them out when you want the window to be open. So they're kind of cool and high tech, and we're just finishing that kind of work up, and there'll be a lot more information about that in the spring after we've done some winter testing on these different systems. But yes, shutters are important. People have asked me, don't I freeze in my living room because of all that glass? No, I don't, because they're triple pane argon-filled windows, and because the radiant heat doesn't pass out, as we talked about earlier in this equation, doesn't go out as fast as it comes in. Could my windows be better? Yes. Are they a problem? No. Our living room is still incredibly comfortable, mostly because of the thermal mass is not all in one spot. It's everywhere. It's radiating in every direction. So whenever you go in our house, my little infrared camera I walked around, besides driving my wife nuts checking rocks, I was always checking the ceiling and the floor. And in my house, there's 2 degrees difference between the floor and the ceiling, because the heat's getting blown everywhere, and it's radiant heat that we talked about. It's like sunlight beaming off of all these things, and it warms up the floor just as much as it's warming up the ceiling. And so temperature wall to wall varies about 0.5 degree, and floor to ceiling is less than 2 degrees. This is when it's 30 below zero outside. So that's another advantage, a comfort level factor with passive style heating and using thermal mass that's really adds comfort to your home. Other questions?
Yes, Karl.
Yes, go for it.
Do you have a slab on grade, or do you have space underneath your house that is heated?
Slab on grade. And I should have talked a little more about that when I talked thermal mass too. You know, that's a real good way to add thermal mass to a house. If you don't like a bunch of rocks in your house or planters with a lot of dirt, Thorsten's house has 1.5 feet of sand underneath the slab, and then insulation underneath that. And it's not insulated between the sand beds. So he lives on the beach with a concrete slab over the beach. And all of that sand he can heat passively with the sun coming in and beaming on the floor. And there's also PEX tubing through it. And so if he has extra thermal energy from his thermal panels and he wants to boost that up a little bit, he can do it that way too. So it's kind of a twofold system. If you eliminate the PEX and just go with the sand, you can still use it. It's just a big thermal mass dump underneath the floor. Total cost, additional cost for a house to do something like that is maybe $500. You know, sand's cheap.
Just to point that out again, I mean, everything we do recommend is thermal mass, basically in slabs. I hate crawl spaces with a passion. I think that they're complete energy hogs. They're not just energy hogs, but also health issues. They're nice storage, but it's hard to get in. It's a concept I've never understood, so we definitely recommend slabs. And for thermal mass, it's by far the easiest and cheapest way to absorb the energy. So yeah, definitely we recommend slabs.
Can you also then use the earth underneath it as part of your thermal mass, or do you have to?
You know, the minute it's uninsulated, if it's not part of your thermal envelope, you're losing all of the energy to the mass surrounding it. You know, our ground temperature is 34 degrees, so it's very cold, and you are completely, you know, it's just being sucked away basically. Over time, the ground certainly warms up, but only to a certain degree. Our soil is just so cold, and you're fighting that physics of hot to cold, and it's just too cold. I mean, there's been studies done where you know trying to store heat energy under the building, but at least 80 to 90% in a normal climate, like in mid-Europe, is bleeding away. With our huge temperature differential, I assume it's even more.
Another, before we move on, we'll get there in 1 second. I forgot to mention, because I wasn't reading my notes as I was yammering along here, a lot of folks think that the insulated concrete forms, the ICFs, are a good way to do thermal mass because you got all that concrete inside that form. That's a misconception, okay? Totally misconception, because the heat that goes into that concrete is not going to re-radiate back into the house because you're blocking the thermal bridge and the radiation with the layer of foam on the inside of that concrete. So it doesn't re-radiate into the house. That's a great way to stop thermal bridging in a wall, actually. It's a technique, is you put foam over something to keep it from being a thermal bridge. And so we want a thermal bridge between our mass and the house so that the heat that's in that mass radiates into the house. We don't want to interfere with that by trying to block any of the thermal bridging from our mass. And so ICFs don't count as thermal mass for a house. It doesn't mean they're a bad thing, but they don't factor into a thermal mass equation. Yeah, your question.
The cross-section of that floor in the octagon, then how many inches of EPS, and then the slab had PEX and a separate heat exchanger in the wood heater, the masonry heater?
The masonry heater has domestic hot water line in it that heats the domestic hot water tank. It's not connected to the floor system directly, although I can use domestic hot water through a heat exchanger to heat the floor if I want in my house. I don't have the sand under my slab. I have PEX in my slab for radiant floor heat, which we don't use, or haven't. We may this year because we've changed some systems, but we never have before heated the house that way. Thorsten's house is different. He's got the sand underneath his slab that I don't have, because I have other thermal mass in my house that he doesn't have. He has PEX both in the sand and in the concrete slab, so he can heat those independently of each other depending on what he's trying to do at his house. Do you follow that? You wanted...
Then you had so many inches of insulation in the floor and a vapor barrier and a 4-inch slab.
Yes. What do you have for what's under your sand? I don't know what you got for.
We recommend 12 inches of EPS, which is an R60 basically. A bare minimum, really, I think, is 8 inches of EPS for our climate, for a decent size.
Karl's did, or you did, how much for Karl?
Karl's is 8 inches. Yeah. That was kind of baseline. Also, we have to follow the timeline. We built Karl's house really was one of our first real test pieces to build a high efficient passive house, zero energy building in this kind of a climate. You know, mine was the next step, and now we moved on and we learned on each and every one of these projects. We learned so much. You know, without Karl's house, my house wouldn't be there. Without my house, other houses which are now out, you know, wouldn't be there where they are. It's just, you know, this huge learning curve which we went through with all of this. But right now, you know, what we recommend is about 12 inches of insulation. EPS insulation will be used for ground insulation, so an R60. Yep.
Have you ever, how would you achieve thermal mass in a floor if the house was built on a site with permafrost?
We just elevated up on pilings. We've done that before. The pilings just need to be a little bit more upgraded, the beams basically which go on it. And we usually pour an 8-inch slab instead of a 4-inch slab on that to increase the thermal mass. That's really what I find the most cost-efficient way of increasing thermal mass. And that's, again, something we really learned big time on Karl's house, that, you know, there's a lot of misconception, in my opinion at least, on thermal mass in cold climates, that it doesn't work, that it is too hard, and that it is really a loss. But that's really contradictory to what our experience is in real projects. And that's where energy modeling is very difficult too, where, you know, we've just recently done a big study on a rammed earth building, which will go up in Anchorage next year for a study just about thermal mass basically in cold climates. And the difference in, we used 4 major energy modeling softwares to model this, and there was 70% difference in the outcomes, which really related to thermal mass. So it's very difficult to have clear answers on some of this, and a lot of it is really based right now on our experience. And you know, where there's certain rules which just, I don't see them apply really in reality from what we see in the field, measuring actual data on these buildings.
So how much sand are you now putting in your most recent?
It's really, that's depending on, you know, a lot of it depends on what is the needs of the client, what is the budget. Sand is a much cheaper medium than concrete, but what I really found is what we do on most projects right now, we just increase the thickness of the slab because of labor cost, because of, you know, the complexity of the foundation. We just simply go to an 8-inch structural slab. Once you do that, you don't have any footings anymore, you don't have any of the extra components you need on a normal foundation. You know, you just basically build a stronger slab, which saves money in labor costs, which for us is very expensive. If I, like on my house, I have about 2 feet, a total of, there's about 3 million BTUs of heat storage capacity I have within my slab. And like right now, the last few days, I load a lot of heat in it, and my house right now is at about 76 degrees, just because I'm overheating from my solar thermal storing actively heat in the slab, which I don't really mind right now. Free energy, who cares right now to be a little bit warmer when it starts getting cold. But it's one concept, heat in, heat out. There is no regulation in temperature really on this concept. You can't put in too much for passive solar. There is a certain amount you can only store by physics, where you're really not seeing the gains. Like we have sensors throughout the whole slab, basically on my building, and there's only a certain amount of depth you really can reach with passive solar heat gain. And once you increase that more, you really need to look into more of an active heating. Like, on our buildings, we like to use solar thermal as an active heating addition to the passive solar, and then we use that as an additional medium. But it's cheap. It's very affordable. A load of sand is very cheap. If labor isn't really the big question, like when you're building your own house and you're putting a lot of sweat equity, I would definitely recommend it. And it's probably, in my opinion, about 2 feet is the max you would want to do. Otherwise, you're starting to, just the complexity of it, you're starting to lose efficiency.
Thank you.
Other questions? Yeah. Oh.
Could you, excuse me, elaborate a little bit about the thermal break at the masonry heaters meeting the envelope? How do you stop bridging there in the masonry heater as it penetrates the roof? It seemed you had a double insulated metal chimney outside the roof there. I don't know if it's a masonry heater or not. I assume so. But about that thermal break at the envelope.
The masonry heater goes up to the ceiling. The rocks end at the wood ceiling in my house, and a standard metal Bestis chimney goes from there. So you do have a little bit of a thermal bridge issue at that point, but the fact that the masonry heater is pulling essentially all of the heat, so to speak, out of the exhaust gas before it gets that far, you're not losing as much up the chimney as you normally would, in a wood stove application, because the chimney temperatures are much lower. You can stick your hand in the chimney at the roof in my house while it's 1,500 plus degrees in the firebox. That's all that heat's getting absorbed by the masonry heater before it gets out the chimney. And is that Dan right there? Nod, okay. He's the guy to talk to. Dan Givens is the guy who built my masonry heater, and he is an expert on such things.
There's no question, it is a thermal bridge. It's a metal piece which penetrates out, and on our buildings, that's really the only thermal bridge I have left, which I can't get rid of. What we usually do is basically we wrap the part of the chimney which goes through the roof, where we're using a cold roof, a truss design basically. We wrap that in rock wool, which basically is fireproof, and we super insulate the stack basically in the cold space. And then for the penetrations where we have the air sealing, we use a fire putty right against the stovepipe itself so that we can air seal it. All our buildings we're trying to achieve passive house air tightness at 0.6, which is very airtight. And the chimney is a very big problem for air sealing, and that's definitely a challenge. And it takes some more extra care on a high efficient building, no question.
We had a question over here. Somebody was. I can't see up there. That's all right.
I was wondering if you've incorporated different temperature zones, like for example, if you wanted a root cellar or a pantry or just a cooler storage area into some of your designs, or if you're really, because it sounded like you're looking at shooting for really homogeneous temperature in your space.
Well, You certainly can zone a house, but you're going to, if you really do an envelope properly, it's something that I was shocked at in my house. When you have a really well-insulated, airtight envelope, the temperature inside that structure will equalize incredibly well. Now in my house, if you remember, the heat source is in the living room area, and then there's a second tier where there's bedrooms, and there's a third tier where there's walk-in closet and Arctic entry and such in the back. My Arctic entry, which is normally the coldest room in a house, is the coldest room in my house, but it's usually 2 degrees cooler than my living room, is all. Even with the air leakage from the doors, the exterior door, which is minimal because I got a good door, yada yada, but still, that's the most extreme case in my house. It's 2 degrees from the living room to the Arctic entry. My walk-in closet off of the master bedroom, so the heat's got to work its way all the way through the master bedroom to that back closet, is usually 1 degree cooler than the living room. Occasionally 2 degrees cooler. I mean, it's amazing how consistent the temperature within the structure is with a good envelope. It will equalize. So if you wanted a cooler area, you would have to work at that. You need to stop the heat from getting to that particular area. But, you know, again, if you're on good ground and you're doing a basement, I mean, there's lots of different variables to work into the equation. But I find the fact that when you have this amount of thermal mass and you have a well-insulated envelope, it's just so incredibly comfortable. Every other home that I've lived in had significant swings in temperature from one room to another and drafts and those sorts of things. And with this kind of a style, you eliminate that, and comfort level is pretty nice. Other questions? Yeah?
Do you have any problem with cooling?
With cooling? Yes and no. The problem we have is you don't want this kind of a house if you have a husband and wife who like dramatically different temperatures in a house and they play thermostat wars where you push the thermostat up and down, because it takes 4 or 5 hours to change the temperature in my house a degree, you know, and you have to work at it. It just stabilizes that curve that we were talking about. I mean, the temperature within the house stays so constant that you have to have a significant energy input or drain one way or the other for a period of time to change the temperature in there. So it takes a little bit of planning ahead, and don't expect that you're going to change it one way or another quickly, because it isn't going to happen. If you've ever taken a warm rock and put it in your sleeping bag, go out camping and take a rock from the fire pit or whatever in the evening and put it in your sleeping bag, it's still hot the next morning. There's a lot of rocks in my masonry heater and in my house, and it's the same thing. I mean, just the amount of energy that's stored in those, it takes a long time for that to drain out. And so, to me, that's the beauty of the equation, and adding to the comfort level factor. As long as you're planning ahead and maintaining that status quo of energy, it's not going to fluctuate quickly one way or another. You just have to agree with your spouse what that temperature is going to be ahead of time, that you're shooting for a target, because, like I say, you're not going to move it up and down quickly. Yes?
2 questions. So you have a slab, concrete slab throughout the whole house, and what kind of wood stove is within your masonry?
The slab is through the entire house. It's thickened on the edges and it's thickened underneath the masonry heater. There is no stove in a masonry heater. A masonry heater is built with fire brick, and I can't encourage you enough to use a masonry heater. And we could do a whole session, and maybe we will sometime. We're going to have Dan Givens come in, and maybe next summer Dan and us will combine and we will do a session just on masonry heaters. They are the best thing going. They've been around hundreds of years. They're super air quality. They burn hot and complete. They're way more efficient. You get much more out of your wood. It's fire brick box. It's built, custom built. Dan builds them. And the concept is to just suck all the energy out of the wood as quickly as you can and store it in the mass of the heater itself. And then it perks back into your house for days, literally, when you have that much thermal mass. So, I mean, they're just an incredible way to heat a house, and from efficiency and whatnot.
Is that baffled? Is it baffled then? It has to go through several chambers?
There's a lot of air passage.
It's not baffled per se, like with mechanical baffles. It's just a long chimney, and Glenn, you should talk to Dan, and he can explain all that, because we're getting a subtle hint with the lights. They got movies and things to go in here, but Thorsten and I will be outside if you have questions.
Thanks so much for coming here and spread the word. We can build good buildings in our community. Thanks so much.